Now this is quite a problem. So if you're seeing for the first time, then you have to pause the video and try it for some time. Try to get an answer and then verify. If you have already tried, then go ahead, watch the video. So what we have over here, we have a wedge of mass m and a small box on the wedge. The wedge is free to slide. There is no friction between the wedge and the ground. There is no friction between the small mass and the wedge. So what would naturally happen? What will naturally happen? Before we jump on to start doing the question, let us just absorb the question. So what do you think naturally should happen? Now obviously, due to the pull of the earth, due to the gravity, due to the weight of this body, this mass is going to come down, and there is a wedge, so it can't come down directly. It is going to slide over the wedge. But since wedge is also free to move, the wedge will go that side. What forces are responsible for that? We should understand that before we ensure ourselves that that is happening. So why is the mass going to come down? It is going to come down because gravity is there. Why it is not coming down vertically? Because the wedge is there. So for that, if you have to draw the forces, then the forces on this mass is 1, the gravity. Nobody can stop that if you are near the surface of earth. And the other force is, since it is on the wedge, it is in contact with the wedge, and it would be pushing the wedge by a certain amount. So there will be a normal reaction from the wedge of the same amount, which is N. So that is, these are the two forces on that block. And if I draw the wedge, then as we thought that the wedge will be moving this side, why would it be moving that side? Because there are forces on the wedge which is compelling. So before I draw it, you tell me what forces will be there. One is the weight of the wedge, which has no responsibility of making the wedge go left or right. This mg is not making it go left or right. What else? So what we have is, this mass was pushing the wedge and the wedge was pushing it instead. So we have an equal and opposite reaction on the wedge. The small mass is pushing the wedge, and that push has to be same as how much it reacted. So this N and that N are ditto same N. They are the same N. So that is an action reaction happening over there. What all other forces are there? Since the wedge is on the ground will be pushing it back. There will be a reaction force from the ground. So let me call that as R. So these are the forces what the wedge is having. Any other force? Can you identify any other force? Gravity is pulling it. This small block was there, so it might be pushing it. We have drawn that. This wedge is lying on the ground, so the ground is pushing it back. So this wedge, like, it feels it is in thin air. It is not going up or down because all the forces in the vertical direction is balanced. So if I have not commented on that earlier, then if this is a block, the block doesn't know that there is a ground below. The block has a force from below. Normal reaction, say it has its mass. Why it is not going down? Because the force is equal to the weight, and hence it is not going down. It doesn't know that this is a floor which is putting a force, or there was some person who is putting that force in. So that is immaterial. So same way, the wedge is not going down because there is R which is countering the weight and the normal reaction of the force. Hence it is not going down. So that's your free body diagram of the wedge and the small mass. So what we see is, this normal reaction has a vertical component and has a horizontal component. There is nobody to counter the horizontal component. Hence the wedge has to go that side. So the wedge goes that side. Now before I go on to solving the question, we'll do little more of analysis. If I ask you whether small questions, let me see who answers it right. Is R equal to mg? Or R is greater than mg, that R what we have drawn, or R is less than mg? What do you say? What do you think? So just 10 seconds for it. I hope you got it right. R is clearly greater than mg. That's the right answer. R is greater than mg. Why R is greater than mg? I think I just spoke that. Because R is counterbalancing mg as well as normal reaction of the vertical component of the normal reaction. This normal reaction has got a vertical component and R is responsible for taking care of both of them. That means your R is equal to not only mg plus the normal reaction's vertical component. Now another quick fire question. Will this R be equal to m plus mg or greater than or less than? I'll give you 30 seconds for it. Think and answer. Another quick one. Will this R be equal to m plus mg or greater than that or less than that? M plus m, both the masses added. So total mass over here was m plus mg. So if this is internal, what I'm asking is this reaction from the ground R, which we knew is greater than mg, is it mg plus small mg? Is this thing mg plus small mg or not? Just analyzing. So I'll give you 30 seconds for it. Okay, let me see. Now, the way I'm going to explain you involves a bit of understanding what is center of mass and all. Now, if R, by the way, the answer is R is not equal to m plus mg. If R was equal to m plus mg, so the vertical forces are m and mg. Those are the two vertical forces. And if these two bodies are considered as one, if those two bodies are considered as one body, then this internal force of N becomes an internal force. So these two have a net external force of m plus mg, and the net external force of the normal reaction here is R. So if R was equal to m plus mg, then these two masses should have been stationary in the vertical frame. But in the vertical direction, only capital mass is stationary, small mass is not stationary. Meaning to say, if I drop my head off down over here like this, then what is going to happen? I have gone down. The rest of the body is here. The head drops down, suppose. Then what happens? The center of mass of the body has gone down. The body has gone down. So here, maybe the center of mass was somewhere at this level. So if the mass has gone down, the center of mass would have gone down, and this has gone to the left, the mass would have gone to the right. With the reference of the ground, mg, the center of mass would have gone down straight, in a straight line. Nothing is going to make it move. So m goes this side, the other m goes that side. The center of mass, wherever it was, just goes down. The center of mass, wherever it was, it just goes down. Why? Because there is no horizontal external forces. So if there is no horizontal external forces, meaning to say if I take my head off and throw it somewhere, then I am going to go back. I am going to go back such that the center of mass, which was in this line, remains in the line. So if I throw something forward, I don't have to throw my head on a frictionless ground. You can try out throwing a heavy bag. You carry a heavy bag and just throw it forward on a frictionless ground. How will you manage a frictionless ground? Just wear roller skates and take a heavy bag. So your center of mass is within your position where you are, the bag and you, and just throw the bag forward. When you throw the bag forward, you are going to go back. Why? Because this throwing action, you and bag, if you consider as one body, then this throwing action is an internal force. It is not going to change the position of the center of mass. So the bag would have gone forward, you would have gone back, but the center of mass would have remained at the same spot in the vertical line. It would have gone down because the external force mg is always acting. So mg will make the things go down, but it will not, mg cannot make it go forward or back. So same way over here, mg is making things go down, but not forward or back. And I asked you whether R will be greater than mg or less than mg. Since the things are going down, since the center of mass doesn't maintain its height, it is going down, that means mg was greater. It means, it clearly shows that the weight was greater than R. Then only it is coming down. So this kind of analysis, obviously it is much required to understand the mechanics very well, and for the later on chapters. So what you see over here is I'm not just solving the question at hand. There are many ways of solving the question. One of the ways, this is a very common question by the way. So one of the ways you will see is people solving this through pseudo forces. Now I have not even introduced pseudo force for you because pseudo force is not an actual force. Pseudo force is a totally bogus force. So I'll discuss that separately in a small lecture. What is pseudo force? So a man, say, standing inside a frictionless truck or trolley. Now if the trolley goes forward with some acceleration, then what happens? This man receives no force if there is no friction on the ground. But in pseudo frame we say that this man has been forced backwards. There is no force on the man. There is no force on the man. Or forget about the man in the trolley. Now the weird thing over here would be man outside standing on the ground watching this truck go with a acceleration. So just imagine in the pseudo frame we say, in the frame of this non-inertial frame, in the frame which is accelerating, in the frame of the bus, we say that the man is having a force equal to mass of the man into acceleration of the trolley. That is so weird that pseudo force is a non-existent force. This man is actually having no force on him, but when we put pseudo forces, we have to write such a thing that the man is having a force of mass into acceleration, mass of its own, acceleration of the trolley. So here also we can apply pseudo force for our convenience when we take with reference to the wedge. But we will do it a bit hard way. I agree that applying pseudo force makes things easier in many cases, but we'll do it in the long way, the way it is a way which will make your concepts clear. So we are going to put actual forces and see the actual acceleration over here. Now okay, before we have a go at this, I'll just set you up by putting a situation which is going to help you figure out this situation in a more vivid manner. So let's quickly look into this situation. We have an elevator which is having a box inside it which is lying on the floor of the elevator, and the elevator is going, say, forward with, say, AY. And what I want you to analyze is this normal reaction on the block, whether it will be more than mg or less than mg. So quickly tell me what will happen. So obviously if the elevator is going forward, this is a frictionless thing, then there is no force transmitted on this, and the body remains over here, the elevator goes forward, so it will be something like this. The block is on the elevator and the elevator goes forward. Block doesn't even know that the elevator has gone forward because there is no friction on the block. So the block remains at the same spot, elevator goes forward, and ultimately it may hit this wall. The wall of the elevator will hit the block, in fact. But what happens to the normal reaction? Since the body is neither going up nor down, the normal reaction will be equal to mg. So a normal reaction is equal to mg in this case. Why? Because if I look just at the body, it had just two forces on it, n and mg. It doesn't even know that the elevator was there and was going forward. The ground has provided a force which is balancing it. It's neither going up nor going down. If the lift was going up, suppose, then the push from the lift, n, is greater than the weight, hence the block also goes up with the lift. So we know that the constraint is that it must be going up with the lift. We write n minus mg is equal to ma in that case. Now next is, if I say the lift was going down and there's no forward acceleration, the lift was going down, then how do you compare your n and mg? You can imagine a spring balance underneath, or you can imagine say ants underneath this. Now suppose the lift goes down, what happens? I think the ants will feel relieved. Okay, you better imagine the weights, imagine a weighing machine underneath it. So if the lift goes down, there's a release in the action reaction over here. There's a relief to the ants over here. The normal reaction is going to become less. The normal reaction is the force with which the block was pushing the ground and the ground was pushing it back. Normal reaction happened to be the mg. It is not mg all the time. It happened to be mg by looking at the constraints that this block was going nowhere. Now in the case that it is going down with say ax, then this block is also going with the floor unless until ax is greater than g. The block will be sticking to the floor because free fall is g. Greater than g, if the box somehow goes with greater than g, then it will be just free falling with g. It cannot keep on lying on the floor. So if the box is going down with ax which is less than g, then what is going to happen is this mg must be greater than n. The normal reaction, the push from the floor is less on the block now because there has been a release. I'll just again show it with this. That's the block and that's your elevator. If it goes down, then the action reaction over here gets a relief. The n becomes less. The n with which the block is pushing the ground as well as the ground is pushing the block becomes less. Means both the floor is going to get a weight less than mg because it is not going to experience the weight of the block, it is going to experience the push from the block. So the push from the block will become less and in return it will push the block less because action has less reaction. If you scold your friend less, he'll scold you back less. If the hand goes down with greater than g, it is going to release. It is going to relieve the block. You can see over here. So the contact is going to go away. That time there will be no push and pull. So there will not be any reaction or action. So if my hand is going down with almost g, little less, say 9 meter per second square, then the push and the pushback is very less. So the push and the pushback depends on how fast the elevator is accelerating down, not the velocity. The acceleration is downwards how fast. So what we get over here is your mg must be greater than n, and equation wise mg minus n must be the mass. Mg is down, n is up, so mg minus n is the net force, so must be equal to the mass into the acceleration of the lift in that direction. So say this was a x, generally vertical we call it as y, so I'll call it a y, so a y direction, it is so much. Now if the lift was going forward with ax as well as down with ay, then what will happen to n? Then what is going to happen to n? So we have already seen that if vertical movement was not there, if it is only forward movement, then what happens is the n doesn't change. It is just going, the lift is just going forward. The lift is just going forward, n remains the same. But if the lift is going forward as well as down, if it is going forward as well as down, then what is going to happen is, because the lift is going down, the block is going to come down. It's like this. So I'll show you. The block goes down. The lift goes forward, the block goes down. So if the lift is going down, the block goes down, then the normal reaction must have become less as explained to you. So it has nothing to do with the forward thing. So here what I'm trying to emphasize is the lift is trying to leave the block. The block is somehow sticking due to gravity. It is staying on the lift, but the lift is trying to leave it. If the lift is trying to leave it, then the normal reaction becomes less. So if the platform is trying to leave the box, then the normal reaction will definitely reduce. So here the platform was a slant platform. So if I'm saying that the elevator over here went this way, down and forward. So if you turn your head and look in the frame, then it is almost this case where this wedge is going that way. If the wedge is going this way, then we can give two movements to the wedge. It is trying to leave this way and it is going that way. So An acceleration of the wedge this way can be broken into two components like that. So that is the analogy over here. This lift I am comparing with the wedge, and we'll be talking about the normal reaction in the same fashion as we have talked over here. So you can just pause the video and think over this part again. Now let us realize that this situation is almost like that situation. What is happening over here is the wedge is going with a certain acceleration in this way. There is no doubt that the wedge will be accelerating that way. Initially it is having no speed, it will pick up some speed, which is called acceleration, so it will be accelerating that way. The responsible force we have drawn over there, a part of N, is the responsible force. So that acceleration is A. But what I am proposing, as I said over here, that lift, if the lift is going this way, we can break the movement of lift in horizontal and vertical. The horizontal was not causing any change to it was not affecting the block at all, and the vertical was changing the normal reaction. So here also I can change the scenario to wedge just sliding by like this. The wedge is sliding by like that and trying to leave the block like this. So we are going to break this acceleration into two motions. One is sliding by and one leaving it like this. So this leaving it this way will be, I'll call it as AY. A capital Y, will figure out the angles, and sliding by along the slide. So are all of you okay with it, that an acceleration which is a vector can be broken into two components which are 90 degrees to each other? One is called AY and one is called AX. Now what I am proposing is that this AX movement, if there's no friction over here, then how much ever AX moves, whatever is the value of AX, is not going to affect the mass mg. That mass, is not going to affect the mass. The mass is going to slide down because of its own weight in this direction, which is mg sine theta. But this moment of the scale is not going to affect the acceleration of m in that direction. What is going to affect the acceleration is this, the wedge leaving it, which is your AY. If the wedge goes down like this, then it is going to go along with the wedge on that. So it is sliding down and going down along with the wedge. It is sliding down, I'll show you again. It is sliding down and going along with the wedge. Yeah, so you see it slides down and the wedge itself goes that way. So it is ultimately over here. So it slides down and the wedge goes that way. So the wedge was going in and the thing was sliding down. The other way to show is wedge was going in and the thing was sliding down. Now the wedge movement is not going to affect the acceleration of the block this way. So that is what we are going to get in the acceleration also. What we are going to get is the normal reaction. When the wedge would have been stationary, the normal reaction would have been mg cos theta. Now do you think that the normal reaction would be mg cos theta? Do you think that this is going to be mg cos theta? So I am breaking the mg into two parts. One is mg cos theta. So I am done away with mg. I have cancelled that. And I have broken into two parts. And the other is mg sin theta. Now, is mg cos theta going to be same as n? No, it is not. N is not going to be mg cos theta. So that what I have told you earlier also, don't blindly put mg cos theta as equal to n in wedge questions, because here it is not going to be same because the wedge is moving. The wedge is moving means wedge is going to go down like this. So it is going to relieve the push. If had the wedge been going like that, it would have been pushing it harder. But if the wedge is going in, if the wedge is going like this, then it is leaving the contact. It is trying to leave the contact. The n will become less. So what we have figured out is n will be less than mg cos theta. So our equations should show that. So I think we are all set to make the equations. So we have the direction of acceleration of the big block. Let us see what is the direction of acceleration of this small block. So the small block I am going to study in two directions, and it will accelerate in both the directions. in this and this, because I don't know exactly which way it will be going. So it is safe to study in two perpendicular directions of your choosing. So say this is x and this is y. So we'll study ax and ay, and ultimately it must be going in there somewhere. As I had shown you earlier, the block was over there, slid down along the y. So it has slided down, but it has gone in also. So it is landing up somewhere over here. So the direction of acceleration, let me just put it like this. That's your actual A, acceleration of the mass with respect to ground. So it has two components. I'll call this component as AX and I'll call that component as AY. So the acceleration in the y direction will be the responsibility of the y direction forces. Acceleration in the x direction will be the responsibility of x direction forces. And ultimately this A would be a vector addition of the two. That means AX square plus AY square. So those are my accelerations what I've figured out. And the acceleration of the big mass is this, again broken into two components. But we are going to write the MA equation of the big mass in that acceleration, in this direction itself. So let us make the equations. The big mass equation is quite easy to write, so shall we write that? So all the forces over here R, N, or mg are vertical except for N. N is a slant force, so it will break into two components. So as told to you earlier, the normal and the vertical makes the same angle as the incline and the horizontal. So I hope you remember that. So the vertical component of N is N cos theta and the horizontal component is N sin theta. The vertical component is N cos theta. Now one of the equation which will be of no use, I'm going to write over here, will be the vertical equation, which is mg is down and n cos theta is down, is equal to r, the reaction from the ground. So that's the big mass vertical equation. Now the force which is actually making it go forward, let's write down that force. It is going forward with A acceleration. And what is that force? The only horizontal force on this block is, now you can see we have no longer this N. What we have is N sin theta, N cos theta, R and R. So the only horizontal force is N sin theta. So one major equation over here, N sin theta is equal to mass of the big wedge into its acceleration is equal to ma. So what all unknowns we have? N is unknown, A is unknown. So not good enough to solve the whole situation, but we have got an equation. We'll call it as equation number 1. Now going on to the smaller block, the small block, and writing the two equations in the direction of 90 degree to the incline and in the direction of the incline. So first one may be in the direction of the incline. We have just one force in the direction of the incline, and the acceleration in that direction we have assumed is AX, and 90 degree to the incline we have called it as AY. So how much would be AX? That is coming from this force mg sin theta. So we have mg sin theta equal to, that's the only force in this direction of the incline. Had there been some friction, there would have been some other force, but this time it is the only force, is equal to mass of the body, which is small m, into acceleration in that way, AX. That's my equation number 2. How many unknowns over here? Only one unknown. So that means we have got the value of AX already. How much is the value of AX? G sin theta. So it tells you that irrespective of how big the mass was, if there is no friction, it is going to just go down. It is going to go down in this direction with G sin theta with respect to the ground. So the acceleration of the mass with respect to the ground along the wedge is G sin theta. That might be a little surprising to some of you who would have used pseudo force for doing it. Now the equation in the 90 degree direction. So to get the total acceleration fully, we need to get both accelerations. So AX we have got, thankfully. AY is yet to be gotten, but we are on to it. So what's the equation in the vertical direction? Equation in the vertical direction is mg cos theta. See, in this direction we have two forces, mg cos theta and n. So who is winning? Mg cos theta is winning. Why? Because it is going in like that. So mg cos theta must be more than n. N has become less than mg cos theta as told to you, as discussed earlier. So mg cos theta minus n, mg cos theta minus n is equal to mass into ay. Now what is this ay? If I have written this equation, mass of this body into ay direction, acceleration in that direction. I've got the third equation, but I am in a bit of trouble. I've got three equations, but I have three unknowns. What are the three unknowns? The three unknowns are capital N, capital A, you have AX, you have four unknowns, and you have AY, and I've got just three equations. You have four unknowns, capital A, AX and AY, and capital N. So how to deal with it? So we have yet not used the constraint. There is a constraint over here. We have assumed that all these bodies were independent as it is drawn. So we have written independent equation. But remember, this body is on that body. So where have we made that use? We have not made that use yet. So the point is, if the body is going in by AY, if the body is going in by AY, it is not breaching this surface. It is not going into the surface. So this surface itself was going back. The surface itself was going back with capital AY. So this small ay and this capital AY is same. This capital AY is equal to the small ay what we have mentioned, because along this direction the surface and the mass is going together. Now that capital AY, thankfully we can get. This A was the horizontal acceleration, AX was along the slide, so that was theta angle, that's your theta angle. So this is 90 minus theta. So generally you have seen me writing 90 minus theta as a dot, so it takes less space, so I'll be using that very often. So what is this? What is this acceleration? This AX equals a cos theta and AY is equal to a sin theta. So instead of AY, we can very well write it as M capital A sin theta. So we have done away with one variable, and hence we have got three equations, three variables, of which equation number 2 was self-sufficient. So that variable we have got the value of that variable, so we have got that answer. So we are just left with two variables, n and a, and we have got two equations. So pretty simple to do. We can just plug in the n value from one into the other and get the answer. So I'm going to do that. But our discussion of this question is not for solving these three simple equations, but to have a deeper understanding of what is happening, and hence we are going to make a vector diagram also of the accelerations and see how the dots are connected. So before that, I'll just solve the equation for you from equation 1 and equation 3. What we get is n is equal to ma by sin theta. So I'll plug it over here and I'll get mg cos theta is equal to ma sin theta plus n, and n happens to be ma by sin theta. So what we are getting over here is a common small m sin square theta plus 1 by by sin theta is equal to mg cos theta. So we have got our a. The a value is mg sin theta cos theta divided by m sin square theta plus m. So that's your acceleration. We can do some variations in the variables and see whether it is all right or not. If small m was 0, if the mass of the small block was nothing, will it accelerate? No, it will not accelerate. So small m figures on top. If you put m as 0, it is not going to accelerate. If there was no gravity, nothing of this will happen. Nothing will accelerate. So if g you put 0, nothing accelerates. It is 0. Okay, so g is not in the denominator making things infinity. It is not. If the theta angle was 0, if the angle was 0, then again it would have been a flat block like this, and just leaving it will not make anything accelerate anywhere. So if theta was 0, this part becomes 0. In fact, if theta was 90 also, that means one block like that and one block like that, then again there is no push, there is no normal reaction, which again makes the acceleration 0. So cos theta is also on the top, making that situation also 0. So this is pretty much giving me a good idea that it is at least the numerator. I am pretty sure we have got it right. So the whole answer must be right. Now, what is the actual acceleration? Now, before we get to the actual acceleration, let me make a vector diagram. Let me get some quantities for you. One is acceleration of the small block with respect to the capital block. I want you to get this acceleration of the small block with respect to the capital block, as if the capital block was not moving. And acceleration of the small block with respect to ground. So I'll just write small m over here. So it represents with respect to ground. So which is this one. So I want you to get this one and that one. So I hope you have got these accelerations using your vector concept, which I'm pretty sure you are quite confident with. See, after a lot of analysis, what we ultimately saw is 3 equations. 1, 2, 3. 3 equations have solved everything. 3 small equations you have to write, but you have to analyze a lot before writing that. So in physics, it is not the length of the work, it is the quality. You have to think a lot, but you have to write precise equations. So whatever your thought is has to be there in the equation, and if the equations are right, your answer will come. So 3 equations, of which one was a standalone equation. So 2 equations and the answer straight away. Now here also, before going into all the vector diagrams and other things, what is asked is acceleration of mass m with respect to capital mass. So I'll again ask you few other questions before you answer this one. The green block and say the orange block. Orange block goes this way with two accelerations, suppose. So what is the acceleration of the orange block with respect to green block? It is still 2. Green block is not moving. 2 was with respect to ground. With respect to green block also it will be 2. Now suppose the green block is going this way with 3. Then what is the acceleration of the orange block with respect to the green block? The acceleration of the orange block with respect to the green block this time will be 2 plus 3. Why? Because we'll assume as if the green block was not moving. So if the green block is not moving and suppose this orange block was having 0 acceleration. If we assume green block is not moving, it will seem as the orange block was going forward with 3. So in the frame in which the green block is stationary, not moving, and the orange block was on top of it, in that frame, it will feel as if the orange block was going forward with 3, but the orange block is already going forward with 2 with respect to ground. So that is added 2 on this, and hence the velocity or the acceleration of the orange block with respect to the green block will be 2 plus 3. So you can do vector diagrams also to get it. And V orange with respect to V green will be V orange minus V green. V orange is this way 2, minus of V green is this way 3. So V green is that way, so minus of V green is that way. So ultimately the vector becomes a 5 vector forward. So what I'm saying is, if a block is going forward with 2 on a slide and the slide itself is going back with 3, then the velocity of the block with respect to slide becomes 2 plus 3. 2 because of going forward and 3 because of the slide going back. So the net velocity becomes 2 plus 3. So over here, what had we discussed? We had said that this wedge itself is going this way with AX. And the block on the wedge is going along the wedge with small ax. That was g sine theta. It was going down with g sine theta, but the wedge is going up. The wedge is going up with capital A cos theta. It is going up with a cos theta. So what is the acceleration of this block with respect to the wedge? With respect to the wedge, as if the wedge was stationary, this must be going down with ax plus capital A in the x direction. So that is equal to your g sine theta plus a cos theta. So a is so much. I'll write a cos theta. We'll write that big thing. A cos theta. So that will be your answer. G sine theta plus a cos theta, where a is so much. So if this is the only question which is asked, you'll have to put the a value, take the LCMs and write it. So that becomes your answer. And what is the acceleration of m with respect to ground? With respect to ground, it will be ax square plus ay square, not a with respect to m square and all. Ax square and ay square. The actual a with respect to ground, which is g sine theta. So that is g sine theta whole square plus ay square. What was ay? Ay was a sine theta, capital A sine theta. A small ay was capital AY itself. So a sine theta the whole square whole under root. So that's your acceleration of the block with respect to ground. Your sine theta fortunately comes as a separate thing outside, so it is g plus a. Units are all g square plus a square. Units are all satisfying. G square, a square are same units, can get added. Under root of that will be acceleration itself. So that's your acceleration of the mass with respect to ground. So these are your two final answers. Now I'll just draw a vector diagram representing all of this. This is the whole work what we have done. We have got the acceleration of the big mass with respect to ground, small mass with respect to big mass, small mass with respect to ground, all in here, and with the help of just three equations. This is a part of solving. So this is just a part of solving. These are the main three equations from where we are getting the answer. So hardly took us any time, and here we have avoided using pseudo forces because I have not introduced the concept yet, and I would recommend you not to use pseudo force as long as possible so that you know what is happening really. This was what is happening really. What is not happening really is in the frame of the body, it is going this way, and the acceleration is so much is in the frame of the body when it is of the big mass. So that is not what is really is happening. Okay. Now, how are they connected? How do I get the acceleration of the small mass with a vector diagram? So let me have a go at it. We'll write an equation for that. Acceleration of the small mass with respect to ground is acceleration of the small mass with respect to the big mass plus acceleration of the big mass with respect to ground. I hope you agree with all of this. So ground, I'll write it as capital G so that you don't confuse with the acceleration due to gravity. The acceleration of the small mass with respect to ground is acceleration of the small mass with respect to the big mass plus the acceleration of the big mass with respect to the ground. So this is the equation, vector equation, which connects this and this and this. The three are connected by this vector equation. Let us see it falls beautifully in the vector diagram or not. So what will be the acceleration of the small mass with respect to the big mass? The acceleration of the small mass with respect to the big mass will have a direction along the incline. Why along the incline? Because with respect to the big mass means as if the big mass was not moving. So if the big mass was not moving, the wedge was not moving, then the acceleration is along the incline. So mind you, AX is also along the incline, but AX is not with respect to the big mass. AX is with respect to the ground. It was going this way. So there some people may confuse, but this AX was g sine theta. With respect to the big mass, it was g sine theta plus a cos theta, because this guy was going down with g sine theta and the big mass was going up with a cos theta. So you had a relative motion, but it will be along the incline. The relative motion will be along the incline. So this vector m with respect to big mass, I'll draw along the incline. So I hope I get the angles almost same. So that's your acceleration of small mass with respect to big mass. Now what is this acceleration of big mass with respect to ground? That is this vector. That's your acceleration of big mass with respect to ground. That is horizontal. So I'll draw a horizontal. So that becomes your acceleration of big mass with respect to ground. So I've been calling it as capital A all the time. So I'll just call it as capital A. This is with respect to the ground. Now this vector plus this vector gives you the resultant vector, which is acceleration of the small mass with respect to ground. So that's your vector diagram. This is your acceleration of the small mass with respect to ground. That is this vector. This vector is this green vector is this one. So this is what we are seeing. It had slid down along the incline, but the inclined plane itself went in, and hence this was your, so I have made the incline a bit too much of incline, but it's okay. So it has gone down the incline, but the inclined plane itself went in, hence the body has gone in. So it had gone down the incline. To make it over here with the orange pen, the mass had gone down with incline, but the inclined plane itself went in. So this thing was acceleration of the small mass with respect to the capital mass, and this is A. So this is your AM. So that is what has happened. Now let me see whatever relation I'm getting over there, I get over here or not. What is the angle theta? What is the angle theta over here? This angle is angle theta, because with respect to the big mass it was along the incline. So this angle is still that angle theta. So if I have to get the AM, I can make a right angle triangle and get the horizontal part of it. So I'll call this much as AX and that as AY. Now can you see from the diagram? So if the editor can zoom in into a bit, I hope. So this is your AX, that's your AY. So in the diagram itself, if this is 90 degree, this side is also 90 degree, in this right angle triangle, what is that AY? That AY, can you see that beautifully, that AY comes equal to capital A sine theta from this triangle. This is the hypotenuse and that's the 90 degrees. So this is A sine theta. So AY was A sine theta, and from the situation also we had said that AY will be A sine theta. AY was A sine theta from the situation already discussed. So my vector diagram is supporting me over there, and what we see is AX might have the same direction of AMM. AX might have the same direction of AMM. It is not the same, and your AMM exceeds AX by how much? How much is this? So I'll write in a different pen over there. This much, this dotted much is how much? That is your A cos theta. So this was your A, so hence this is your A cos theta. So we see that AX plus A cos theta is your AMM. So was that not the case? AX plus AX is G sin theta plus A cos theta was your AMM. So my vector diagram is telling the whole story again. It is giving me all of what we have written over there. So that's how your vector diagram is. That is how the velocity in which it is actually moving. So if you ask me whether it was required or not for the question, hardly all of this discussion was required, and we could have written just these 3 lines and we could have got the answer. But to know what is actually happening, by the way, if you have done in pseudo frame, you wouldn't have got all of this. You would have got only one part of the answer, which is AMM. You would have got only AMM in a go, and it more must have been required to do. You would have used this equation again after getting AMM. And knowing A, you'll have to find A, and then you would have got the actual acceleration. But this way we are getting all the things together. So this vector diagram is something what you need to observe and absorb how it is happening. So in all other cases also, if you are able to visualize and make the vectors, it would be good for you. It will be a good way of solving and understanding the whole situation. So right now we are not having an exam practice, we are not having a speed practice. What we are doing is a concept strengthening session over here. So I'll ask you to do a question which is involving almost all the same things apart from one extra thing. So you'll have to be careful about the constraints over there. So that question is the same way I'll draw it. You have a wedge M which can slide on a frictionless ground, and you have a mass small m on it. But then this mass is tied with a rope which goes over a pulley, and the rope is attached to a fixed point. The pulley is attached to the big mass. So we have done the constraint of this question in the constraints chapter. Now I need you to solve for all these things: acceleration of the small mass with respect to ground, acceleration of the big mass with respect to ground, acceleration of the small mass with respect to the big mass. And if you can show me the vector diagram, how all of them are falling together, that would be great. So that's your homework. Thank you. I hope you have understood this question and you have got the point that it is just not solving the question but analyzing all the aspects. Just two bodies, no strings, nothing, and still so many things to analyze to get your mechanics right. So to understand the physics more beautifully.